If you have not already, this is a good time to go back and review that video that reviews how to simplify radicals. That's really going to come into play today when we're trying to talk about complex numbers. Section 1.3 complex numbers is important because we've been talking all about real numbers throughout this unit so far. And in order to solve more types of problems, we just need more numbers. We need more types of numbers, and the next set of numbers would be complex numbers. What we're trying to do today is to simplify imaginary numbers, write complex numbers in standard form, and perform operations like multiplication, division, subtraction, addition on complex numbers. We've been talking about solving equations, and a solution is what makes that equation true. If we look at this equation that's written here, x squared equals 1, it has two solutions, 1 and negative 1. We know that those two are solutions because if we sub them into that equation, they make it true. If we look at the equation though, x squared equals negative 1, there's no way to find a real number that will square to make negative 1. 1 squared is 1, negative 1 squared is 1, and so there's no real number that will make that true. That's why we need the set of complex numbers or imaginary numbers. The first imaginary number, or the imaginary number, is the square root of negative 1, and that's equal to I. It's notated as I. Another rule of thumb, if I equals the square root of negative 1, if you were to square both sides of that, you would get I squared equals negative 1. That's another very important thing to note. That will come up here in a couple of slides as well. All right, all this means is anytime you have a square root of negative number, any negative number, it's going to end up having an I in the answer. So if I had, for example, the square root of negative 25, we talked about in that simplifying video, you can break it down into its parts. 5 and 5 have buddies. So the square root of 25, if the square root of 25 is 5, the square root of negative 25 is 5i. If the square root of 9 is 3, then the square root of negative 9 is 3i. Anytime you take a square root of a negative number, you're going to have I in your solution. All right, if you have a problem that you can type in the calculator, you absolutely want to do it. We talked about last class, or last lesson. If you did the square root of 25, if you can type in your calculator and get a nice answer, absolutely do it. The square root of 25 in the calculator is 5, and so the square root of negative 25 is 5i. The square root of 12 in your calculator, though, does not give you a nice answer, and so you'll have to make a factor tree. 12 breaks into 4 and 3, 3 is prime. 4 breaks into 2 and 2. 2 and 2 are both prime. We can write those out in numerical order, 2, 2, and 3, and try and find buddies. Again, go back and watch the review video if you haven't yet. The 2's have buddies and they get to go outside. The 3 does not have a buddy, and since this was a negative, it has to have an I with it. The I always goes outside of the square root. Notice on this answer, the I was not in a square root. On this answer, the I is not in a square root. You always want the I to go outside the square root. On problem C here, 13, we try and break it down. 13 is actually prime. It's just 1 and 13. There's no other way to break 13 down. So 13 we can't simplify, but we cannot leave a negative inside a square root, so we just have to take it out as an I, square root of 13. When you multiply or divide radicals, we talked about in that review, the square root of A times the square root of B equals the square root of A times B. That holds as long as A and B are not negative. If A and B are negative, you do have to take the I out first before you go and do those operations. So on the first one, can you take the square root of 9 in your calculator? Yes, you can. It's 3. Can you take the square root of 25 in your calculator? Yes, you can. It's 5. Since those were both negative inside the square root, they have to have an I with them. And now we can do the multiplication. If I had x times x, it would be x squared the same way here. I times I is I squared. And if you go back 2 slides here, remember that we said that I squared is always equal to negative 1. If you ever have an I squared in a problem, you want to change it to negative 1. So this is 15 times negative 1, which is just equal to 15. I'm sorry, negative 15. So this answer right here simplifies to negative 15. Same exact thing we could do here. The square root of negative 15 is I square root of 15. The square root of negative 3 is I square root of 3. That's a times symbol. We remember we have a times square root of a times square root of b is the same thing as square root of a times b. So this is the same thing as I square root of 45. Then we can break our 45 down. I'm going to start moving a little faster here. 9 is 3 and 3. So this would be 3I square root of 5. The I always goes just before the square root. The I, all it did was come down. This 45 is the same as 3 square root of 5, 3 root 5. The same issue with division. We can divide them, but we have to take the imaginary numbers out first. So that's I square root of 50 over I square root of 2. You know x over x just divides to 1. In the same way, anything over anything the same is going to divide to 1. The I over I will divide out. Square root of 50 divided by square root of 2 is the square root of 25. The square root of 25 is just 5. Simplify each expression. So now all of these have just been imaginary numbers, right? We just have a single number. No addition, no subtraction in the end. A complex number, all that means is that we have a real portion and we have an imaginary portion. We have a portion with an I and we have a portion without an I. You always want to write those separately where the real portion is by itself, a plus or minus sign. The imaginary portion is by itself as well. In example A, the square root of negative 100 is the same thing. The square root of 100 is 10, so the square root of negative 100 is 10I. And notice that's already in that form A plus BI. That plus is actually plus or minus. It doesn't matter if you have a plus or a minus there. In Alex, if you get a question, if you get an answer that looks like this, let's say you did quadratic formula or something, you get an answer that looks like that, all you're going to do is break it up into two fractions, so you have your real and your separate parts separated. All right, here's what we're going to do. So all we're going to do is break it into two fractions. That's 2 over 5 plus 7 over 5I. The denominator just stays with both of those fractions, and that is it. Now we have it in A plus BI. That's all we want is to get it in this form, A plus BI or A minus BI. All right, answer or problem C here, negative 6 over 9. If I do it the same exact way, plus square root of negative 18 over 9. The square root of 18, I'm going to do some scratch work over here. That's 2 and 9, 3 and 3. 3's are buddies, get to go outside. The 2 doesn't, so negative 6 over 9 is staying the same, plus 3I square root of 2 over 9. We had to have an I because that was a negative, right? The square root of 18 broke into 3 square root of 2, and the I had to come out because it was negative. Now simplify those fractions. You can divide all those things by 3. We're talking about things that are not inside the square root. You can ignore what's in the square root. So if you divide everything else by 3 here, you get negative 2 over 3. Divide everything by 3 here, and you get 1I square root of 2 over 3. And now it's in A plus BI form. This I always goes before the square root. We say it's A plus BI like the B always hangs on to the right side. It's not technically wrong if you were to write the I there instead. Just classically in math, you put the I before the square root. All right, next we can perform operations on complex numbers, but before we do that, we need to know what the powers of I are. We know that I is just I, right? I to the 1 is I. I squared is negative 1. That was given to us on that first slide. Once we get past that, we can extrapolate from there and say I to the third. I to the third is the same as I squared times I, right? 2 and 1 makes 3. I squared is negative 1, I. So that's just negative I. I to the third is negative I. You'll see that in this chart here. I to the fourth is the same as I squared times I squared. Same as negative 1 times negative 1, which is the same as positive 1. I to the fourth is positive 1. If you keep following this chart down here, you're going to notice a pattern where we have I, negative 1, negative I, positive 1. I, negative 1, negative I, positive 1. Notice that that pattern just repeats itself over and over. And so we can use that pattern to actually simplify higher powers of I as well. I'm going to show you on the next slide how to do that. For any power of I, since we know the pattern, all we're going to do, here's the trick. I'm just going to show you the trick here. We're going to take the power out of the 48. We're going to take the power and divide it by 4. And then depending on what the remainder is, or depending on what the decimal part is going to be our final answer. So if you take the power, 48, divide it by 4, what you get is an even number, an even 12.0. If you ever get 0.0, whatever number 0.0, that means it was evenly divisible, okay? The same thing as having I to the 4th, and it's just going to be a positive 1. If you ever get a number 0.25, your answer is going to be a positive I. If you ever get a number 0.5, your answer is going to be a negative 1. And if you ever get a number 0.75, your answer is going to be negative I. So on this one, 48 divided by 4 gave you 12.0. We can just follow the chart here, and we know that that's equal to a positive 1. I to the 23rd, I'm going to say 23 divided by 4 in my calculator. You're always dividing by 4. 23 divided by 4, you get 5.75. And 0.75 relates to a negative I. 50 divided by 4 on the next one gives you 12.5. 50 divided by 4 is 12.5. That relates to this column, which means our answer is going to be negative 1. And negative 19 divided by 4 gives you negative 4.75. Again, the 0.75 relates to negative I. When you're trying to add or subtract complex numbers, all you're going to do is combine like terms, just like you would if you had variables. So on this one, I like to clear the parentheses first, right? So if you distribute a plus into that, it's not going to change anything. Distribute a minus into that, it's going to change all those signs. Negative 2 minus 4i plus 5 plus 2i minus 3 plus 6i. And then combine your numbers. Again, we're just combining like terms here. Negative 2 plus 5 minus 3 is going to give you 0. Negative 4, here, let's get a different color here. Negative 4 plus 2i plus 6i should give us plus 4i. If either of these pieces are 0, you can just ignore it. So our final answer here can just be 4i. Here it says subtract this from this. That means we need to subtract this number minus this number. 3/4 plus 9/5 I minus 1/2 plus 2/3 I. Same thing as the last problem, we need to distribute the negative in. 3/4 plus 9/5 I minus 1/2 plus, oh, that negative needs to go to both, minus 2/3 I. This is a good point to use your calculator. 3/4 minus 1/2 would give you 1/4. 9/5 minus 2/3. I'm going to type in my calculator. 9/5 minus 2/3. Change that to a fraction. And we get 17/15 I. When you're multiplying, you're doing the same exact thing with variables as well, where if you multiply I times I, you get I squared. The one thing you need to be careful of is if you ever do get I squared, you need to simplify that to negative 1. So if you distribute that negative 1/2 in, what you get is negative 2I minus 3I squared. That's the same thing as negative 2I minus 3 times negative 1. Remember that I squared is the same as negative 1. And that's the same thing as negative 2i plus 3. If we want it exactly in that form, a plus bi, we would call it 3 minus 2i. We're just going to change the order but keep the signs the same. On question B, you're going to FOIL. So multiply outside times outside, negative 2 times negative 3i. I'm sorry, first times first. Negative 2 times 4 would be 8. Outside, negative 2 times negative 3i would be plus 6i. Inside would be plus 24i. And then the last times last would be negative 18i squared. Combining those like terms, that would give you 30i. I'm going to go on and change this I squared out for a negative 1. We know anytime we have I squared, it's the same as negative 1. 8 plus 30 I plus 18. The 8 and the 18 can combine to make 26 plus 30 I is our final answer. You never want an I squared in your final answer. You never want a negative under a square root in your final answer. Here's another example of this. 3 plus 4i squared. 3 plus 4i squared, anything squared is just that times itself. Like x squared is the same thing as x times x. Here, 3 plus 4i squared is the same as 3 plus 4i times 3 plus 4i. Pause the video for a second, see if you can solve this. This is what that solution looks like. You FOIL to get this line, combine like terms, change your I out for a negative 1, combine like terms again. Same exact thing here. This one's a special case where we have what's called conjugates, right? So we have a 5 plus 2i, 5 minus 2i. They have the opposite sign in the middle. When you FOIL here, you end up with that top line. Combine like terms, and the 10i and negative 10i will actually go away. I squared turns to negative 1. 25 plus 4 is 29. All right, the last operation we're going to talk about here is dividing complex numbers. If you're ever dividing complex numbers, you don't want an I in the bottom. Notice with this problem, you ended up with no I, right? You ended up with no I, and that's sort of what we want, and that's the strategy that we want to use. If you ever multiply by the conjugate, 3 plus 5i, you're just taking the same exact thing, but with the opposite sign. It should get rid of all your imaginary numbers in the denominator. Let's see what happens here. FOIL across the top and FOIL across the bottom. On the bottom, every time this should happen where you have a plus and a minus of the same thing. On the top, you can combine like terms. I'm just going to go on and call this right here 10 times I squared is the same as 10 times negative 1. I'm going to call it a negative 10. Negative 25 times negative 1, I'm going to call this positive 25. That's going to save me a step of writing. So 24 minus 10 would be 14. 40 plus 6 would make 46i. On the bottom, 9 plus 25 would make 34. Then if you can divide them all by the same thing, you should. These are all even, so we can divide them all by 2. And that's our final answer. If you want it in the form a plus bi, say Alex or Pearson will not let you submit your answer like this, you're just going to break it apart into separate fractions like we did earlier. 7 over 17 plus 23 over 17i. Anytime you have a negative exponent, that's the same thing as writing 1 over that thing. It's the same as flipping a fraction. So here we would say that's the same as 1 over 2 plus square root of 3i. If we want to multiply by the conjugate, we would multiply by 2 minus square root of 3i. 2 minus square root of 3i. I'll keep working through this problem with you. On the top, if you distribute the 1 in, that would be 2 minus square root of 3i. I wish they had written it as I square root of 3, and I think I'm going to start writing it that way from now on. So I square root of 3, that just looks better to me. When you FOIL on the bottom, you get 4 minus 2i square root of 3 plus 2i square root of 3 minus I squared square root of 9. So you're multiplying the square root and you're multiplying the i's together. There's not a whole lot you can do at the top, but on the bottom you have a plus and a minus that go away, which is what we hoped. You have an I squared, which is a negative 1. So that's negative 1. The square root of 9 is 3. So altogether, negative times negative 1 times positive 3 makes a positive 3. On the bottom, our like terms are 4, and positive 3 makes 7. There's no way to simplify that, but if we did want to write it in that a plus bi form, it would be 2 over 7 minus I square root of 3 over 7. It could also be square root of 3 over 7 I. And that's it. Like I said, these are going to help us when we go to solve quadratic equations. When we go to solve quadratic equations, a lot of our answers are going to be complex numbers because we do want two answers. Sometimes we just can't get real answers to solve them.